testing, right? So I think like based on the input from the different labs and other different phases, so now there is an evolution of the treatment. It's basically, the old paradigm. The doctors used to give a drug and say, okay, if it's not working, they will switch. So basically, it's like a trial and error prescribing sometimes because it doesn't suit every patient all the time with the right drug in the first choice. So the idea is to bring like efficient medical care, which is like a new paradigm which now every hospital is moving into. So I think the advantage of this new paradigm is this is going to help in selection of the optimal therapy, and also this will also reduce the trial and error prescribing, and this will help to avoid adverse drug reactions, and this will improve the quality of life, and also reveal the additional or alternative uses for medicines or the drug candidates. So I think what we do in our high-throughput phenomics as well as in a Ram Dasgupta lab here in GIS is, I think Ram is the one who is completely coordinating this effort of precision oncology. So he had a lot of collaborations with the local hospitals here, which is National Cancer Center or SGH. So he has a close relation in working with Dr. Gopal Iyer and Dr. Ian Daniel from ACCS as well as GIS. So when the patient comes to the clinic, the patient tumor is implanted in mice as well as, and they were trying to expand it as a primary cell culture. So this is like sometimes we will directly derive this is PDPC, this patient-derived primary cells, or sometimes then like we will grow them and we will also barcode them and we are maintaining a biobank of this. And when these cells are multiplied in a larger scale, this will subject to high throughput screen. So then whatever the data we are seeing in this, which will be further validated in the PDF model, and so whatever the data output we are getting in this, the response data will be shared with the doctors to help or guide the treatment strategy for this particular patient. If he or like if they are coming back to the clinic with a relapse setting or with the kind of a resistant model, actually, I think that time this model will be useful. So the next slide. So here I'm going to discuss like how our models are closely represent the patient tumor. So you can see our gene expression data. Like this is the patient, right? The tumors which are exercised from the human. So we have subjected to gene expression analysis, and this is you can see which is 0.97, which is for the when the same tumor when it is growing in the mouse model, and this is our cell line which is 0.95. So the advantage here is actually what we are seeing, the expression correlation between our models, three different models actually, is completely highly correlated. And also we have tested this RNA expression. It's also similar across different models, which is close to 0.9 to 0.95 across different settings. So which is kind of giving us the confidence that I think the tumor complexity which we are seeing in vivo condition, which is still mimicking at the level of pretakes, that's also the patient-derived primary cell line models. So which is very, very useful for testing the multiple drugs from the particular cell line models. So we expanded the cells in a lab. So then what we did, like we used to do is like we used to test them against the set of FDA-approved anti-cancer drugs, and then our initial data showed some of the specific compounds which are working on a specific patient tumor lines here. So these are all like a different patients like HN137, 120, 148, 159, and 160. So then we will like what we did, like whatever the expressions we have seen, so that is also correlated with the molecular gene signatures which we found, like say some of the drugs which we found as a CDK inhibitor as a pathway, and we have also seen there is a dysregulation of this particular pathway which we can find in the same similar cell type, and also our subsequent validation in the same patient-derived xenograft model has shown that these compounds, whatever we found in vitro screen, is showing a very good correlation in the in vivo setting also. So this gives us the confidence that whatever the output which we are seeing from this data should be useful to the clinic, or like this can be a basis for a translational research. So I think Dr. Ram and Gopal, when they were working on one particular patient, so they found that gestatinib can be more effective to this patient based on the data which we have seen in the lab. You can see this data, which is more effective for this particular patient tumor line, and then we tested them on the in vitro model as well. So there also we have seen There also we have seen this receiver regression. So then based on the co-clinical settings at NCCS in Singapore, Dr. Gopal has tried this particular medicine which we have found that which is showing a better response compared to the other standard of care. And we have also seen basically this although the data which we have seen in the in vitro condition it clearly works in the clinic, at least in the N equals to 1 co-clinical trial setting. So I think this is one of the best example of how we can develop this phenotype-driven precision oncology. So right now what we are trying to do is we are trying to increase the numbers. We are trying to increase the number of patients here, and then we are trying to add like a genomic and epigenome and gene expression and drug response data. We wanted to use this as a machine learning tool to find out, suppose if we do this for 25 different types of patients, maybe we will come back with a novel biomarker or like a novel signature that can predict again the drug response in a real time to the patients. So that is a hope for us to put more effort on phenotype-driven precision oncology and GIS. And so after that particular portion, so what I wanted to show is, so apart from our focus on 2D models and 2D models and then 3D models, and then how we use those models to do the oncology approach where we can find out how the specific drugs are working for it. So here I'm going to show you some quickly like what all the different other work which we are also doing, like using high throughput or high content screening methods. I think what we are trying to do is, I think Dr. Judith Ko, she's our computational genomics platform leader. I think she put this she developed a database. It's like a chemical pathway profiler. So what it then does is like we are trying to create a bio-CV for these set of molecules. I think here we have worked close to around 15,000 compounds. We have tested them on like different pathways like ERK, WIT, CMYC, and JNK, and all the pathways. I think you can see these clusters which are showing like the compounds against the specific pathway activity. So which will be useful for the small selection of small molecules, or you can identify like how one similar scaffold is showing multiple effects. So this is an example of how this web interface can be helpful to the different scientific community. When they reach us, I think we can show them that okay, like they can select some of the pathways which are upstream or downstream. They can select a very focused library based on this particular effort which we have put on different compounds. They can identify the compound connectivity map, like say they can infer the relative target of uncharacterized compounds. So this will be an additional step which will help them to select the particular compounds. And this is another image-based drug screening which we have done. So in which the cells are labeled with different colors, and like we have tested them with a set of FDA-approved anti-cancer library. You can see like how these particular cell lines are reacting to these. Like we have also worked with, I think the previous study which I have discussed is with the oral squamous cell carcinoma, and this one is the colorectal cancer. So I think we are coming to the another one. This is the platform where I'm leading here in Singapore, which is ChipGIS. It's called as Center for High Throughput Genomics. I think our effort here is, I think we are working and supporting the different investigative programs in giving expertise in the automation and miniaturization. And also we will do a lot of chemical and functional genomics, and we do gain of functions and loss of function studies using CRISPR or shRNA, and we have different annotated libraries for small molecules as well as functional genomics. I think people who are interested to screen or like to know more about high throughput and high content screen, you can follow our website, which is chipgis.astar.edu. So this will give you the clue of what we are doing here on a day-to-day basis. And this is the companion computational platform which is led by Dr. Judith. I told you because she's developing a lot of infrastructure development, because for all the high throughput screens, if you don't have an end-to-end solution, the data will look really redundant, because I think all our high throughput screens data has been gone through this pipeline, and she will bring in this the ease of analysis and also the interpretations to move forward. I think this platform is very, very useful to give an end-to-end solution for all high throughput as well as all image-based screens. So with this, I'm ending this presentation. I would like to acknowledge Dr. Ram and his team in GIS Singapore, and Dr. Gopala here and his team in NCCS Singapore, Dr. Ian and Dr. Daniel at GIS and NCCS. And I would like to thank my team from Center for High Throughput Genomics, and I would like to thank Dr. Huck, he's Executive Director, GIS Singapore, and I would like to thank Dr. Jonathan and also the team for this wonderful support. So with this, I would like to end this presentation. I can take up questions now. Thank you.
Oh, cool. Thank you, Dr. Suriasamy, for your presentation. A quick reminder for our audience on how to submit questions. Simply type them in the Q&A box down by clicking on the green Q&A button at the lower left of the presentation window. Dr. Suriasamy will answer as many questions as time permits. So the first question is, how do you determine which signaling networks or pathways are to be investigated or screened in your current study? For example, oncogenic, metastatic, anti-apoptotic, and immune modulation, etc.
Yeah, this is a very important question. When we do a phenotypic screens, sometimes we may not know the direct target engagement. I think the way we do this part of pathway analysis by high-sensitivity biology approach, using the Phoenix system that we have from the